When we're looking at rotation, we've said something about kinematics. Sort of the next step on our journey is going to be looking for the equivalent of F equals ma and kinetic energy 1/2 mv squared associated with rotation. So what's the rotational equivalent for this, and what's the rotational equivalent for this? Because that'll take us to our force and energy. And this gets to why we even have different variables for rotational motion. I mean, after all, V works perfectly well. If I have something that's going around in a circle, I can talk about its velocity, right? It's at that point, right? Or if I'm on this line, I can talk about the velocity here. The difference is that the velocity is different the further out you get, because in the same amount of time, in one revolution, this outside one goes 2 pi times its radius, which is bigger than this one, right? If this is the halfway point, this is half the speed. But in both cases, your omega is the same. So omega is the same for a rotating object for any point, but V is going to be different for different points. And that's why we go to omega and alpha instead of V and A. So you can imagine that instead of this, we're going to want to do this in terms of alpha, and we're going to want to do this in terms of omega. And it turns out to be easier to start over here with the kinetic energy. So let's look at kinetic energy and consider not maybe a circle, but at least start with just a couple of masses that are on a really light rod or string. And so we say we've got a mass here, M1, and we've got a mass here, M2, and they're connected by something that's so light that we don't have to worry about it. And they're going around in a circle, right? So they're going around like this. It's a fairly big circle, and this is the axis of rotation, right at the X is the axis. And so notice the kinetic energy of the system, would be 1/2 m1 v1 squared plus 1/2 m2 v2 squared, right? But if I want to write this in terms of omega, I could say kinetic energy is 1/2 m1 V, our connector here is that V is equal to R omega. So these have different R's. So I would call this R1 and call R2 like that. So this would be, V1 would just be R1 omega squared, right? Plus 1/2 M2 R2 squared omega squared. Now I can kind of combine these to say kinetic energy equals 1/2 m1 r1 squared plus m2 r2 squared times omega squared. And then what we do is we go, okay, that's the mass equivalent, right, for this equation. This we call I for moment of inertia. So this is moment of inertia, and it has units. So the units of this I are kilogram meters squared because it's mass times this. And the moment of inertia is just taking all the masses that are in an object and multiplying it times the distance from the axis of rotation, this r squared, and just adding all of those up. Because it matters in terms of rotational kinetic energy how close a mass is to the center. If you take the same mass, if M1 and M2 are the same, and you try to swing it around a 1 meter string versus a 2 meter string, this is harder to do because it's further out to get it going, okay? And so this is a way to describe that. So in general, the moment of inertia is, if we have lots and lots of points, like we're doing something like this, lots and lots of points, we can say the moment of inertia is equal to the sum of all the masses times the radii, however many there are. this sum goes from 1 to n to how many points. And if we've got a uniform material, this turns into an integral. Okay, before you panic, I'm not going to make you calculate that. What I'm going to encourage you to do is look up the moments of inertia in the table online or in your book. In your book, the table is figure 1020 in your book. And that's a useful figure to just have somewhere. In general, on any test, I'll just provide that figure for you. I don't expect you to memorize these. I want to point out, for example, we can look on that table and say, what's the moment of inertia of a rod? So if we look at a thin rod, and we, whoops, and we rotate it around the central point, if you do that integral, it turns out that the moment of inertia is equal to, I have to look this up, in the middle, it's 1/3 the mass of the rod times the length squared, so this is L. And so what you've done is you do the integral to add that up. But if you take a rod and swing it around the end, so around here, the moment of inertia, sorry, the end is, and the middle is 1/12. Around the end is 1/3 ml squared. And notice the difference between these and middle is that the moment of inertia around the middle is equal to 1/4 the moment of inertia around the end. So it's a lot less, and you can test this out for yourself. If you take something and you, a stick or a pencil or pen, and you rotate it about the middle, that's fairly easy to do. And if you rotate it about the end, it's just not as easy to do. And so when you do that, you can actually feel the effect of the moment of inertia. And this is really apparent with something fairly long, where this L, which is squared, starts to come into play. So we just look these up on the table, and then this is sort of our equivalent for mass. So our equivalent for mass is moment of inertia. That's going to be the case over here. And then what we're going to need to do is find out what our equivalent for force is. It's related to force, but it needs to be a little bit different for our rotational, for Newton's second law. And it turns out that just for completeness, what we have is something called the torque. Okay, and you're going to see about that soon enough. But the torque, the sum of the torques equals I times alpha. And kinetic energy of rotation is 1/2 I omega squared. And the reason that is so useful is that we can know the omega of any one of something that's rotating, like a fan blade, for example, on a turbine. And then we can know our omega and get our kinetic energy. And we don't have to find the kinetic energy of all these parts that have different velocities.